Hello YouTube viewers, welcome to my show Rocket Monday. In today's episode we're going to take a closer look at hypergolic propellants. So let's dive right into it. Now first thing you have to understand, what is the problem with our current one. Now we currently majority time we either use kerosene plus oxygen, hydrogen plus oxygen, or in future we will use methane plus oxygen. Now what is the problem with that? Now you have to understand, for fire to occur, basically something to ignite, quote unquote, it has to have three things being fuel, oxygen and heat. Now because of the inherent nature of liquid oxygen, inherent nature of liquid hydrogen, these things are extremely cold. So if you let basically liquid oxygen come in contact with liquid kerosene, it's gonna freeze the kerosene. And in case of basically SpaceX, they cool liquid basically kerosene itself. So kerosene is already in very serious risk of basically freezing up. So how do we make sure that it catches on fire rather than freezing? We have to have what we call independent ignition system. Now of course there are 10,000 ways how people handle it, how people do it, but you have to understand there must be an independent system. You cannot rely on the fact that there is oxygen, you cannot rely on the fact there is oxygen plus fuel and they are in a what we call stoichiometric ratio, basically the perfect mix of oxygen versus fuel. It's not gonna catch on fire automatically, you have to ignite it. So let's say in case of very old rockets like in Saturn V era, some rockets literally used to have a matchstick shove up to their basically rocket cone, and some person's first job was there to just go there and ignite it. This was very old. Then electrical ignitions was started and they put wood automatically will catch on fire before the rocket engine started its fuel pump. So once the fire is lit, everything is confirming that yeah, wood is on fire, then they will let the fuel and oxygen flow, and then it will catch on fire. Now you can understand that is a very messy system and not very reliable. So then in case of Saturn V, they had a specific chamber that will ignite it, and in case of basically Falcon 9, what they have is a third propellant. Basically that third hypergolic fuel is there just to ignite it. It's only there. That green flame that you see many times before the engine start is there for that purpose only. That is very reliable. So they flush the fuel, that third fuel, and it automatically, the moment liquid oxygen comes in contact with it, does not matter if it's a liquid form, solid frozen form, or it's in gaseous form, it will catch on fire. It is that reliable. So people use that, but you have to understand, this means there is a risk of what we classify as hard start. What does that hard start mean? Think of this way, liquid oxygen is very dense. Any fuel you are using is inherently dense, whether it be methane, whether it be hydrogen, because liquid hydrogen is used, it's very dense. So even few milligrams of it, let's say, is spooled up in somewhere, let's say in turbo pump or injector plate, if it's there and is spooled up, like it's not burnt, and you burn it afterwards, let's say it was flowing, because there is a fuel pump and it's continuously flowing, instead of flowing properly and burning, there was like a small second, as in like few millisecond of delay was there between the fire and fire being lit and the fuel flowing. That gap causes what we call hard start. So basically there would be oxygen, there will be basically fuel, and it will not burn up. The moment you ignite it, it will burn up, but it will explode. That causes what we call hard start. Most rocket engine will flat out blow up because of that. So we generally make sure we keep igniting it before even fuel comes in. So that's why you see green flame so easily. You're inherently not supposed to see it, but to be on the safe side, to make sure there is no hard start, no explosion going on, they make sure they flood it before, like they flood the system with before they let liquid oxygen go, they flood the system with the third propellant. Of course these are happening in milliseconds, so we humans can't see it, but for a computer standpoint, the first command would be flush the system with hypergolic, then flush the liquid oxygen, and then of course liquid oxygen plus the fuel will be opened up simultaneously to make sure that there is no risk of hard start. On top of that, let's say you figured all these things out, they are very hard to restart. So igniting them, you can understand, is so complex. Now imagine once you don't have enough fuel pressure, or once you are in space, things are not as easy as they are on surface. Reigniting them is also an issue, because once you are in 0G, let's say you are letting your propellant go, of course there are nozzles for that. Now that nozzle may not mix with another fuel, like it happens in 0G. So reigniting them, of course engineers have to go back to the drawing board to make sure it's reignitable reliably. So there is a lot of hassle you have to do with these things. And in terms of complexity, this is the core reason why rocket engines are expensive. To give you a context of this, many people say that space shuttle, that big rocket that had, like, it had spark wheels, like wheels that were firing sparks. People say that was for ignition. No, the ignition chamber was inside the engine. That was only there because they were using liquid hydrogen, and such a large amount of it, some liquid hydrogen is inherently is gonna leak out. To make sure that it does not pool up around that area and, like, have a hydrogen based environment there and just one spark and it blows up, to make sure that leaked hydrogen is never become an issue, that's why those spark plug was there. There was a basically electrical spark plug system built into the engine itself. That RS-25 engine itself had a spark plug chamber, small chamber. Basically it was a miniature rocket engine that was there, that was ignited using electricity. Once that ignition has done, then it will trigger the full engine thrust. So you can understand, it's ludicrously complex. Then we come to hypergolic solutions. Now you have to understand, when I say hypergolic, I'm not referring to one thing. Hypergolic simply means something that you mix and it automatically ignites. Basically it could be nitrous oxide mixed with something else, it could be peroxide mixed with something else, it could be nitric oxide mixed with something else. So that is why we always classify as hypergolics. It's not like when you say LOX engine, basically you are assuming liquid oxygen is used. So in case of hypergolic, it's not necessary. You can use hypergolic in many scenarios. Sometimes you can have it hypergolic itself used as an ignition, like in basically Falcon 9, or sometimes you use it as a main rocket itself, because it spontaneously ignites the moment you connect it. So that two part, you don't have to worry about the third part, that heat part. The moment they come in contact, they're gonna ignite 100% of time, 100% reliably. There is no margin of error here. This will work. This is absolute. And all you have to do for ignition, like instead of having giant small rocket chamber inside a big rocket chamber, you don't have to do that. Just open the valve and it will automatically catch fire. Basically mix for ignition. So fuel and oxidizer, you just have to keep them apart so they don't blow up, and mix it, boom. So in terms of restarting, again, it's super easy. As long as they both come in contact, they will catch on fire. You don't have to worry about, like, it pulling up in zero gravity or things of that nature. There is nothing to worry about. The moment these two touch, it happens. And it's very simple. Now if you are familiar with school drawings of, like, basically rocket, you will see simple things like, you have oxygen tank and you have fuel and you have rocket engine. This is how simple that is. Basically the simplest form of rocket that you can build in your home would generally be a hypergolic rocket. You cannot, like, it barely even needs turbo pump most of the time. So okay, that's the engine, that's the fuel. How do we implement it? Now you have to understand, when I say you don't need a turbo pump, does not mean you can directly run it without any issue. You still want to pressurize it. The reason for that is, like, if you have fuel, whatever it is, be it methane, be it butane, be it kerosene, be it jet fuel, whatever you have, unless you burn it very fast, you're not going to get thrust out of it. So that is why your gas stove does not go into the ground, because it's still doing the exact same thing. It's still mixing oxygen, it's still mixing the fuel, but it's not doing it fast enough. To get that fast enough, we pressurize it. Now in case of pressurizing, this is one scheme that you will find in Wikipedia. Now I want to explain this. This is not necessary how every rocket works. This is one of the most commonly used ones. So what we do is basically have a third tank. Now you might be like, isn't this again going back to the same problem with those things? Yes and no, because there also you have to have this third tank no matter what you do. So instead of having a fourth tank for ignition, you have what we call pressurizing gas. We generally use helium. Why helium? Helium is very, very, very inert. This is the core reason for that. It will not react to anything. So you cannot use hydrogen with oxygen. You are making an explosion right there. So for this reason, we have what we call tanks, which are pressurized with helium. Now helium, let's say the tank pressure would be, let's say 50 psi or 100 psi. Let's go with 100 psi. So what we'll first do, we'll open the valve with oxidizer and fuel, but only little bit, let's say 1%. We just open it, just go there. Like the moment it catches on fire, the heat exchanger, basically you have to understand, rocket chambers go very hot. So this helium that's circulating around is also cooling basically the rocket chamber, so it does not melt, but it's also gaining in pressure because you have added heat to it. So that 100 psi that was coming in from a pressurized tank now become to like as high as 200 or 500 psi. Now that high pressure gas is now fed into fuel tank and oxidizer tank, and at this point the moment computer detects there is enough pressure in the fuel tank and oxidizer tank, it opens the valve completely. Now even more fuel is there, even more heat is there, and more helium is coming from the tank. Even this valve is also opened up to full capacity. This creates a continuous cycle. Now, benefit of that, it's very simple. All you have to do is control valves. There is no pump for this. It's very simple, elegant, reliable, and it's super quick also. You have to understand, because there is no ignition stage. Is the moment you send electrical impulse, the moment, of course, as long as your valve gates can open very quickly, you're gonna get thrust. So there is no time like, oh, there is stages, let's flush the system, let's flush oxygen, now let's flush the fuel, now make sure that it's ignite. There is no like, you touch it, boom. So it's very, very quick, and the quick aspect is very needed in space once you are in space. So you have seen big rockets going to International Space Station, okay, fine and dandy, but once you are in space station, you're not gonna ram directly into a space station. You have to align it. To align that, you need small thrusters. If you have seen the recent Dragon capsule test, you must have seen small rockets doing course correcting. So for course correcting rocket, you don't need a lot of thrust, but you need agile system, basically a system that is like, you gave me 1 Newton here, 10 Newton there, 15 Newton there, like, and it's happening multiple times a second. It's that quick. You have to be quick. The Hypergolics does allow you to do that. And there is another benefit. I specified that hypergolic is a mixture, and many times it can be directly mixed with liquid oxygen, but you don't have to do that. There are other combinations. Most hypergolic combinations are non-cryogenic. Basically, if you put it in a craft, you can forget about it for some extent. Basically, if you are familiar with rocket launches, you must be familiar with the fact that rockets are always empty. They are only loaded up with fuel and oxidizer basically few seconds from launch, because if they didn't do it, the fuel will evaporate. So to make sure that does not happen, this non-cryogenic mixture is very safe, because it's non-cryogenic, aka you don't have to freeze it. They can be stable as upwards of 70 degrees Celsius. So you have to just make sure you don't heat it up in an oven, and it's gonna be safe, it's gonna be sound. That is very necessary. That is also crucial aspect. Once you go into space, it's not gonna freeze up on itself, and also it is not gonna heat up once solar radiation starts to bombard it. So it is very, very stable. So again, pressure fed, valves for control, super quick, and non-cryogenic. These are the benefit aspect of it. Then we come to the aspect why people use it. It's very reliable. Now it's used in everywhere. To give you a context of this, Saturn V, basically a liquid oxygen plus kerosene rocket, at its upper stage, basically the lunar stage, the thing that actually landed, relied on hypergolic. Why? Hypergolic engines does not have enough thrust. You have to understand this aspect. You cannot, like, you can make a rocket, but it's not very efficient. Basically the specific impulse, aka mileage, is not very high. So either you have to use too much of it. So in case of moon, because the gravity factor itself is 18% of compared to earth, it's more than efficient. So they use that, and it is 100% reliable. People landed on the moon, they got off the moon reliably. You don't have to worry about this. This is that reliable. Then we come to space shuttle. If you are familiar with the backside of the space shuttle, you must have seen there are 3 big engine bells basically, and there are 2 small ones. Those 2 small ones are this, what we call hypergolic. These are used, so once they go into space to do the final maneuvering, sometimes this could have been used for reboosting the International Space Station and deorbiting burn. So you don't need a lot of kilonewtons here. All you need is basically something reliable, something cheap that can be quickly deployed. So as you can see, they have pressure tanks, and they have the oxidizer tank, pressure tank, and the fuel tank. So all you have to do is very simple. You just have tanks and valves to control it all. So from space shuttle to Saturn V to this current basically taxi to International Space Station, basically Progress spacecraft, Russian spacecraft, this also has it, and this has been used reliably for last 50 years, and it has been constant service. This is one thing that is completely human rated. Everybody knows it, everybody knows how to use it, and this is what we currently use as of now to reboost International Space Station reliably, and basically every year we do that. So it is very tested, very reliable. Like, it is reliable on a level that cannot be expressed in any other system. So okay, if it is that reliable and that good, why don't we use it more? Well, it's very toxic, aka few milligrams of it in air, like in proportion, you dead. You breathe it, you dead. Then it's corrosive. Now this is the most problematic aspect of it. Let's say you put it in a tank, and I told you it's a liquid in room temperature. It's still gonna corrode your steel tank, no matter which tank you use, made of polymer, made of anything, it corrodes it over time. Of course, it's not like you put it in a tank and it's like instantaneously destroys it. It corrodes it, and you cannot have a very thick tanks like this in a rocket system. Basically this itself will weigh too much, and because of the specific impulse, aka not having enough thrust per liter of the fuel, you have to have basically very thin fuel tank. Basically you try to make it as thin as possible to reduce weight. So because of that corrosive aspect, there is an inherent expiry date to fuel tank itself. So once you, let's say in case of Dragon capsule, you put in the fuel, you have to make sure you throw away that fuel tank every 6 months. And that is why Progress spacecraft is always cycled through. So once if you are familiar with International Space Station emergency protocol, there is always 1 to 2, sometimes even 3 craft docked there, just to make sure that in case of emergency they can easily let go of his space station. To make sure that things are there reliably, stay active in case of emergency, they cycle it. So the reason why they are cycling it is because if they let one Progress craft stay there permanently for a very long time, the fuel tank will be compromised and it will blow up the moment they fire the engine. So to make sure that does not happen, they keep cycling it. They cannot put the craft in space and forget about it. So Dragon can also suffer the same fate. That's why it has a maximum space life of 6 months. Basically that fuel tank will be compromised if they put it longer than that. Now of course, when I say 6 months, it's not like one day before 6 months nothing is bad is happening and the moment 6 months is over, boom, it blows up. It's not like that. It's corroding, but all the testing suggested that till 6 months they are 100% reliable. The moment 6 months is over, it starts to go 90% reliable. That is not acceptable. So that is the 6 month shelf life. Basically once you park it in International Space Station, if you want to leave it as a basically lifeboat, you must use it or send it back to Earth before that 6 month period is over. That is the corrosive aspect. On top of that, if that too was not bad enough that it is toxic and corrosive, it is also carcinogenic. Basically, if this even few nanograms of it reaches your bloodstream in one aim, like let's say go through your skin, go through your lungs, or mixed in the drinking water or anything like that, it's gonna give you cancer just for extra bonus. Like killing you directly is not enough. Corroding your, basically it will dissolve you if you ever fell into this. That's also not enough. It's also going to give you cancer just for good measure. So it is very, very problematic to deal with. And you can see the suits that are used for handling this sort of stuff, they are so expensive. They will make high-end firefighting suit look like cheap. Like they are so expensive simply because they have to make sure it's corrosive. They have to make sure it's hermetically sealed because you cannot breathe in, and it's all a whole different level. So whenever space shuttle landed, there was some crew, basically the ground crew, whose job was go there, basically poke it with a stick and flush the system out, so they can make sure every little bit of peroxide is removed from the system, so that area can be safe. Before this step is done, you are not allowed to go to near space shuttle once it has landed, because even though most of the fuel has been spent, even few milligrams is very lethal. So there was those people whose job was just to go there, flush it out. So there are certain problems with hypergolics. Now some people are working with certain mixtures that are not this problematic, but they again suffers with the consequence that they are not very powerful. So some versions of this is still in use and they will always be in use because this is very reliable. Everything else aside, it is reliable. And in terms of corrosion, we figured it out that we give it a tank that is thick enough so it can last for let's say 6 months, and we'll make sure we cycle it every 4 months. So that's how we are handling as of now. So whenever somebody says like that's why Dragon capsule exploded, I really doubt it, simply because they know it, or worst case scenario that happened, because of its corrosive nature, it may have corroded somewhere and salt water would have gotten, and then kaboom, things could happen. Even Thunderfoot has also made a video about this, and I really think that is the reason, because this rocket has been tested. Basically, Dragon's system has been tested. It has been put in International Space Station. It has been tested to death, and including the emergency abort system has been tested, including the fact max Q testing has been done. So there is only one reason why it could go boom. Or worst case scenario, there has been some very deep design flaw that exposed itself. Now, if that happened, that's awesome, simply because that means the next version of it will be much more safer. Now, if seawater happened, that only causes one problem, that they have to either flat out scrap the idea of reusing the basically capsule, or they have to reinforce it. So these are the problems. Because of the corrosive nature, it's not very long-term solution, and this was a time where ICBMs were using this sort of fuel, but then they realized like even the 6 months of active time is not enough. Then they ditched it and they went to solid rocket motors. So this was my presentation on hypergolics. I hope you liked it, learned from it. In that case, please leave a like, click the ad that are shown in this video, that will directly help me. And if you didn't like it, you can press dislike. I would urge you to press it twice to show me your extra disappointment. And please leave a comment because I reply to all of them. Subscribe, press the bell icon if you are free, and as always, thanks for watching.